In this separations video, I've planned to show you an example stripping column problem that has to do with reducing the mole fraction of an extremely toxic nerve agent from a stream of water. So the flow rate of water is specified at 20 moles per minute, and it initially contains 1% of this hazardous impurity. You wish to reduce the concentration to 0.2% or less. Perform the separation in a stripping column at 1 atmosphere with a gas flow rate of 70 moles per minute, and the Henry's law constant for SOMON and water and gas is 0.4 atmospheres per mole fraction, and you can assume that it's constant. Find the number of stages you need and the outlet composition of the gas. So very subtly, this is actually two different questions. The first question, find the number of stages you need, is a design type problem, and the outlet composition of gas is a predict type problem. So I'll show you how to navigate both. Before the video started, I just translated the information that was given in the problem statement to the appropriate cells in Canvas. So we know what L is, we know what X in is, and we know what X out is, except I made a mistake there. That should be 0.02. We know what the vapor flow rate is. We know what the composition in is, so we assume that there's no SOMON in the inlet stream. And we don't know what Y out is. That's one of the questions that we're asked to answer. We also don't know what N, the number of stages, is. That's another thing that we're asked to answer. We do, however, know that the Henry's law constant is 0.4 atmospheres per mole fraction and that the pressure is 1 atmosphere. So the first thing I like to do in solving these problems is to just graph the data that we have. And in this case, we can plot both the equilibrium line and the operating line. So please learn the difference between a plot of data and solving equations. So plotting data, I'm just choosing various x's. Right, so these x's don't correspond to anything in the column necessarily, but I start at 0 and I choose a range of x's that will encompass all the x's that I think that I'll see in the column. Right, so I think at maximum I'll see an x of 0.01, and at minimum I'll see an x of 0.02. So 0 is indeed below what I expect to see in the column, the lowest possible concentration I'm likely to see in the column. And I should pick values that go all the way up to 0.01 or more. And I have that here. So the equilibrium data looks like equals H, that needs to be $signed, times X divided by P, also needs to be $signed. I can double click that formula all the way down. And I've set up my spreadsheet such that it plots the data for me. Now remember that scaling of data is something that you may need to think about. Contrary to distillation, I don't want to go all the way from 0 to 1 because that's going to be a lot of range of the plot that I don't use. So I'm going to only plot the portion of the plot that I expect to be relevant, which is 0.01 to 0.002, and actually a little bit below that as well. And you'll see what I mean in a moment. The operating line is described by the operating line for the stripper, which I've clipped from my OneNote notebook. So that is equals L over V. So L divided by V. I'll put that in parentheses. And because Yn is 0 in this case, I can actually factor out the L over V. So it's L over V times Xn, which is going to be that X, minus X out, which is constant. Okay, and that is going to give me an operating line. Let's see, I'm not freaked out by the negative here, but I am freaked out that I have divide by 0 in value, and it is because I did not $sign my V. So I have to be careful to keep those variables constant. Again, I'm not as concerned about the negative value here. I think that's okay. Let me just double check. Yep, that looks good to me. And I can tell that it looks good because my x-intercept is 0.002, which makes sense. All right, so I've got two operating lines here, and this graph makes I hate the way this graph looks. So just know that I'm bothered by the way this graph looks, but I'm not going to fix it. Just know that I expect much more professional looking plot than this. You need axes labels. You should clean this plot up a little bit if you mean to turn it in. All right, so next I'm going to answer the question of how many stages do I need? And in this part, I already have plotted the data, so the only thing to do is to step my stages. So I'm going to do that with with Excel over here. So I'm going to have a column for stage 1, 2, 3, 4, 5, and I don't know how many stages I need quite yet, obviously. I'll have a Y, which will be in. So actually, I need to start at stage 0. This will be like my liquid coming in. I do know what that is. All right, this is going to be equal to my X in. Let me zoom out slightly. You know what? Okay, I just rearranged my spreadsheet a little bit here. So stage 0 isn't actually a thing. I just put stage 0 because X in is going to come from above the column, and that's why I put that there. All right, so X in comes from above the column. What do I know from here? I know that Y, I don't know Y out, actually, right? I'm going to have to start from the bottom of the column here, I think. So I'm going to keep, need to rearrange this. Maybe we'll go from the top, or I'll just start from the bottom. I might need to add more stages. I'm just doing the stepping thing, right? So let's say we have a 6-stage column. My Y in is going to be 0 from the bottom. Let me get rid of this as well. All right, I've inverted this hopefully for clarity, but hopefully it doesn't confuse you. So I'm inverting it because I have to start at the bottom of the bottom of the column, because I know what X out needs to be, and I also know what Y in must be. So Y in comes from below the column, which is why I have a blank row here. And X out must be 0.002 or less, right? But I know that this is the absolute lowest that it could possibly be. Now from here, I'm going to step upwards through the column, even though it's down in my Excel sheet, until I reach an entrance composition that is 0.01 or greater. So I'm going to alternate stepping through. So my Y is going to be in equilibrium with my X, which I know is H times X divided by P. So there's an equilibrium relationship between the vapor coming off of stage N and the liquid coming off of stage N. Now that I know my Y, I can now calculate the N from the Xn from the next stage by solving this equation. So if I rearrange this operating equation to solve for Xn, and I'm doing that because I know what Y of n plus 1 is. So that's going to be equals V divided by L. So I had to multiply through by V over L times Y of n plus 1, and then a plus X out. Right, so I need dollar signs on this cell because X out does not change. And I also need dollar signs on L, and I need a dollar sign on V. So that is my formula for the next X. And now I can drag that all the way down, and I can drag my Y's all the way down. And I'm going to keep going until I get to a stage that the X coming from it is greater than 0.1. So N minus 3 happens to be where that is. So let me plot this data set. So insert, and whoops, I'm going to insert it here. Select data, add X values and Y values. And for this data series, I don't want the line, I want the markers, like that. Okay, so let me adjust my formatting again. Okay, that's looking good. Maybe not. Okay, so you have to imagine the steps here. So I just cleaned up the formatting a little bit, making it so that it was easy to see. So you have to imagine that my steps are starting here on my operating line, as I always start, to my equilibrium data, over to my operating line, equilibrium data, over to my operating line and equilibrium data. And if I step one more, then I'm going to be beyond 0.01, which is what I want. So these 3 data points are corresponding to the 3 stages that I need in order to perform this separation. So 3 stages is my first answer. Now my second question is a predict type problem of what is the outlet composition of the gas. In other words, it's not simply where this coordinate ends up, because that is going to surpass my inlet. So actually, for a predict type problem, I remove the specification of X out because I can't specify what comes out of a 3-stage column. Once I build 3 stages of a column and I put X in and Y in at the specified flow rates in, then my output becomes specified. So now what I have to do is remove X out as a specification and instead guess and check until I reach 3 stages. So you can see how changing X out will change what my operating line looks like. So I can choose several different X outs. Not quite that great. Right, so by moving this line, you can see how it would be affected. So every time I have to start at either Y in or X in. So I can start at either side of the line. And because I know there's 3 stages, let me amend this. I'm actually just going to make a new one over here. All right, so because it's a separate problem, I actually made a separate chart for what my compositions are going to be. And this is reflective of my actual situation. So this is all I can control about the problem. Once again, I can't control what X out is going to be. So once I have my known input from both sides, so I know that my liquid comes in at 1% and my vapor comes in at 0%, now I can code up my sheet just like before. So I can take my equilibrium data and my operating line and plug in formulas for Y and X. So Y of n plus 1 is going to be equals the stripping section, the stripper operating line. So it's equals L divided by V, and those don't change, multiplied by X n minus 1 minus X out. And this is the one that I will have to guess and check. So I also need $signs there and there. All right, so I'm going to make this a highlighted cell because this is going to be one of my inputs. And you see that if I guess 0.01, let's see what happens here. So my X is going to be solved with the equilibrium equation, and it's Y is H over P times X. So X, therefore, is Y times P divided by H. Okay, so I'm going to copy that down and copy this down. Now you can see that when I copy this down, my Y that I get is not 0, but it's 0.003. And this tells me that my initial guess was wrong. So this is where I'm going to, again, use goal seek. So what if analysis? Goal seek this cell to be equal to 0 because I know that this is what it must be by changing the value of the cell in this column. What happened? Change this to 0 by changing cell there. Huh. Okay, I think goal seek is misfiring on me, so let's try it the old-fashioned way, and that might actually be illustrative too. So I've moved my data over to give me these X and these Ys. And again, this corresponds to, I'm choosing, we actually plot these points instead, plot the operating line points. So I'm starting at 0.01, so I'm starting at the top of the column now, and it doesn't matter which way you choose to start. You could do this problem either way, so that would actually be a good thing for you to go through and try. Try setting the opposite constraint. So try starting at Y is equal to 0 and going to X is equal to 0.01. So I've got 1 stage, 2 stages, 3 stages, and on my 3rd stage, this is going to be my composition out. And this is not Y is equal to 0. I think what's happening is that goal seek thinks this is close enough to 0, and that's why it's giving me this answer. So let's try guessing something else. Let's guess 0.0005. That was way too much. My mind doesn't work well with small numbers. But if I try 0.001, that's not close. Let's try 0.2. Moving in the right direction. I want to go until this fourth point is exactly on my axis. Need to go a little bit further. I'm getting close now. Oh, too far. And that's pretty good. All right, so 0.0014 looks like in 3 stages that my y is close enough to 0. So if I start here, which corresponds to y is equal to 0, yn is equal to 0, which I know to be the case, my corresponding x out is going to be 0.0014. So with 3 stages, I'm actually going to get a little bit better. Notice I'm still on specification because I'm still less than 0.2%. So I got 1 stage, 2 stage, 3 stages, and I would call this problem solved. Depending on how precise you wanted to get, I'm sure if you added more significant figures here, you could get it closer. Maybe not. Let's try 4.2. Yep, I think that's going to be good, right? That's right on it. So this is what actual composition I would get coming out. Wait a minute. Oh, no, I'm right. Okay. This is my actual X out, but the question asks, what is the outlet composition of the exit gas? And for that, all I would have to do is look at this one. So this is actually what's coming out of the column. So Y1 is coming off of stage 1, and therefore the outlet composition of gas is going to be 0.2% as well. I'm confusing myself now. Oh, I got it. I was confused, but this is a coincidence, right? The outlet gas is going to be 0.246% is outlet gas. And I was getting confused because my specification was 0.2 or less. But remember that you can't constrain that. You can only set up the number of stages and set up the vapor and liquid flow rate. Now, if you wanted to, after you design a stage with 3 stages, instead of having a column that gives you a outlet liquid that is less than what you specify, so that's still good, right? But maybe you say that you want to send less air to the column. You can actually turn this vapor flow rate down a little bit, and you can still be on specification. So then you can still play guess and check. So if I turned vapor down to 60 moles per minute, for example, you can see what would happen. So the reason why I gave you this Excel spreadsheet, by the way, and what I encourage you to do is use this as like a simulation. So I showed you that somebody else had already built the McCabe-Thiele calculator online. To my knowledge, nobody's built an absorption stripping calculator. But if you have the Excel knowledge, you have the tools to be able to make your own calculator. You can play with this and look at different scenarios, and you can get an intuitive understanding of how this column is going to work. So with that, I'm going to conclude this video. Hope you enjoyed watching, and I'll see you in the next video.